Hello everyone, this video is called Local Linearity, and it is the idea that most functions, when you zoom in at a point, look like a line, therefore locally linear. So we're going to go back to a couple of our functions that we looked at when we looked at categories of functions and talk through what local linearity means for these different functions. So I have my function f of x already graphed here. Actually, let me put on projector mode so that it is nice and big. There we go. So I have f of x graphed here. And when I say that the function is locally linear, what that means is I can pick a point along this graph, and if I was to zoom in at that point, I would eventually get a line. So I'm going to go ahead and take the point 1, f of 1. It's the point right here. I'm going to go ahead and label it. And what I'm going to do in Desmos is I'm going to go ahead and zoom in. And I'm going to zoom in using this plus key. And every time I zoom in, I'm going to make sure that my point is at the center of my screen. And as I zoom in, notice that my function is looking more and more like a line. Now that's pretty good. What I have right here looks very much like a line. And what can we do with lines? Well, we can identify the slope of a line. And so if I wanted to figure out what the slope of this line is, there are a few different ways that I can do it. The first is I can remember that slope is the ratio of the change in y over the change in x. And if my increments are the same in both my y and my x, meaning my boxes have the same width as they do height, which I can see here that they do. Yes, so my width and my height of my boxes are the same. Then what I can do is I can pick 2 points on this graph that intersect these little boxes and count the rise, the number of boxes that I go up, over the number of boxes that I go over. So if I'm going to look at this line, because it's a line, I know the slope is the same everywhere, I'm going to start at this point right here. I'm going to go up 1, 2, 3, 4, 5 boxes, and then I'm going to go over 1, 2, 3, 4, 5, 6, 7. So my rise over my run is 5/7. I'm going to go ahead and just put that as a note here. So the slope of the line at x equals 1 is 5/7. Another way that I can determine what the slope of this line is I can pick 2 points on the line and find the change in y over the change in x. So just for simplicity, I'm going to pick the point at x equals 1.05 and the point at x equals 0.95. Now the nice thing about Desmos is that it evaluates functions for me, so I don't have to type in what the y coordinate is when x is equal to 1.05. I can use my function notation to find that. So I have my y2 minus my y1 over my x2 minus my x1. And this is very close to 5/7. Now, another way that I can do this in Desmos is I can use the following notation. I can use f prime evaluated at x equals 1. What this notation means is find the slope of the line when we have zoomed in at the point x is equal to 1. Some of you have taken calculus before, and you might recognize this as the derivative at a point. And yes, it is the same thing. For right now, though, because we're just working on these big ideas, I want you to think of f prime of 1 as the slope of the line if you were to zoom in at x equals 1. Notice that the units of a slope are the units of y over the units of x. And so therefore, those are the units of f prime of whatever my x value is as well. There's going to be another video that only deals with units, but I just wanted to get you thinking about that. So now, what is the significance of this slope? The significance of this slope is it tells us how quickly our function is changing at that point. So in a previous video, I talked about how to read graphs dynamically. And so the slope of a line that we get when we zoom in at a point is a measure of the steepness of the function. So if I was to zoom out, this value right here is a measure of how steep the function is at this point. If you're wondering why these two numbers aren't equal, it's only because when we zoom in to see a line and find the slope, we're approximating that because we're eyeballing it. Okay? This is actually the exact slope. So you should see a difference here, a very, very small difference. You should be in the ballpark. So now what I want to do is I'm going to graph a line that has the same slope as our local line here and goes through that point on our function. So I've already kind of found a nice equation for that. And so I just want to show you that if I was to zoom in at this point, the line and the function are right on top of each other if I zoom in far enough. Okay? So if I zoom back out, this line has the same slope as this function does locally. And this purple line in mathematics, we call the slope of the tangent line. Sorry, the slope we call the slope of the tangent line, but this line we call the tangent line. So sometimes you might hear the expression, the tangent line. A tangent line has the same slope and goes through the same point at the point we're interested in. Okay. If you were to zoom in over here, you would get a negative slope. I wanted to go ahead and try and see what happens if you were to zoom in at the point 0, 1. What is the slope of that line? You might think that it is fairly obvious that if we were to zoom in somewhere along this curve, it would look like a line because this function looks a lot like a line. So what we're going to do now is we're going to consider our other function, g of x. So g of x looks like this. Yeah, let's keep it like that. And this function certainly doesn't look linear, especially at the point found at x is equal to 2.25 and our y is equal to our function g evaluated at x equals 2.25. It is definitely not looking linear right around here. But we're going to go ahead and we're going to zoom in right at that point. And as long as we zoom in far enough, we will get a function that looks like a line. So this function is locally linear at 2.25, at x equals 2.25. And we could find the slope of this line using the same methods that we did before. I need to check and make sure that my increments are the same in my x and my y. Notice that Desmos puts the x values up where the x-axis is. And these look fine, so I could pick 2 points that look like they go through these box intersections. And I could see that my slope would be rise over run, so 1, 2, 3 in the negative direction, so -3 over 2. I could also pick 2 points that are around here to find the slope of the line. So why don't I go ahead and pick 2.26 as my x, my first x, or my x, I'll call it x2 because of the way that I'm doing this, and 2.24 as my x1. Don't forget that our function that we're looking at now is g of x, so therefore I need to make sure I use the notation g. If you start using f, it's going to refer to this original function. Now I'm going to divide this by x2 minus x1. And I have a slope of negative 1.46. And I could go ahead and see how that compares to the actual slope, and that is pretty close. So the slope of this line at x equals 2.25 is negative 1.46. I could go ahead and graph the equation of that line, and what you'll see here is that I actually hadn't zoomed in far enough to get it perfectly overlaid. And that's fine, because what we're doing when we're zooming in is we're getting an estimate. And getting estimates is something we're going to be doing a lot of these first few weeks before we develop the mathematical tools to get the exact values. So I could zoom in a little bit more, and then you can see it is indeed locally linear. To be locally linear, there just has to be a viewing window where if you zoom far enough in, you see that it does indeed look like a line. Now, if I was to zoom back out, then what I have here, my purple line, is my tangent line to this point. A tangent line is always tangent to a function at a point. So this is a tangent line at this point. And this tangent line shares the same slope that we have when we were to zoom in and get this local line. It also shares that point. So it shares the point and the slope. Even though from a zoomed out perspective, these look nothing alike. So you can do this with a lot of these different functions, and you can try out exploring the slope of functions at different points with these other examples from class. But before we wrap this video up, I do want to let you know that there are functions that are not locally linear. And what I'm going to do very quickly is give you an example of one. So I'm running out of names, but I'm going to call this one a of x, and it's going to be the absolute value of x. Now, the absolute value of x is actually a piecewise function that is equal to x when x is greater than or equal to 0, and the opposite of x when x is less than or equal to 0, or sorry, less than 0. Now, if we were to zoom in anywhere along here, we would get that our function is locally linear. But if we pick this point, 0, 0, so I'm going to put the point 0, a of 0. If we zoom in at this point, notice that no matter how much we zoom in, we never get a line. And we could just keep on doing this over and over and over. And we will unpack what are the properties here, or what are the features of this function that lead it to not be locally linear. But I just want to draw your attention to, okay, this example so that you know not all functions are locally linear. So you can keep zooming in, you're not going to get anywhere. And let's see what happens if I ask Desmos for that slope, and I get undefined. It doesn't exist. So we're going to kind of keep unpacking these ideas. This concept of locally linear should be something that has visual meaning for you, that you think about in terms of graphs. So when you're looking at a graph, when you're thinking about how steep is this, you want to think about zooming in, even if you can't actually zoom in, zooming in visually and seeing what does it look like if I was to zoom enough that it would look like a line, the function would look like a line. What is the slope of that line? How does that compare if I'm looking at two different points? If I want to go back to my original function, how does the slope compare at x equals 1 and x equals 4? Is it steeper at x equals 1 or x equals 4? And the way that you answer that is you visually zoom in and you see which one has the steeper slope if you were to zoom in for it to be locally linear. I encourage you to test out with some of these other examples and see if what you're finding with your local linearity matches your intuition.